Awesome, thanks. All right, so I noticed in the billing for this, I was billed as Matt Ahrens, ZFS creator. And you conveniently left off the article there. It's definitely a ZFS creator. There's a lot of folks who worked on this, and I started on ZFS when I was straight out of college in 2001, and I definitely did not create this all by myself. But we'll get into more details of that later. Back in the day, 13 years ago, 2005, we released ZFS into the world, and we went around saying the goal of ZFS is to end the suffering of system administrators. We wanted to make everything in ZFS work well together. We wanted there to be no sharp edges, so you aren't going to run one command and then, oops, I totally misconfigured everything. We wanted the configuration to be resilient, meaning that you don't have to make all of your decisions up front. If your needs change, or God forbid you made a mistake, you can correct those mistakes easily with ZFS. That's what I said. So I wanted to take a look back and say, like, how did we do on that? Looking back over the decade plus. So I think no surprise, a creator of ZFS thinks that we did a good job. I think file system as the administrative control point has worked really, really well. Inheritable properties lets you, configure things really easily, tell the system what you need. There's lots of flexibility. We have 3 different kinds of quotas and reservations. That's regular quotas, ref quotas, and user quotas for anyone counting at home. It's easy to add storage. Everything happens online. You can add and remove special devices to accelerate performance, like log and cache devices. Storage is easily portable. You can take it from one operating system to another, and between releases as well, with great backwards compatibility. So where did we fall short? One thing is that we have lots of properties, lots of configurations, but some of those properties only apply to newly written data. So you can kind of get out of this by doing a send receive or copying your data. It's not there's workarounds, but it's not perfect. That especially with things like dedupe, where the performance impact of that can be really long term, even after you've turned off dedupe, because your existing dedupe blocks are still in the dedupe table, which is still impacting it. The second place that I think we've fallen a little bit short is that you can't reconfigure your primary storage. So if you add the wrong disks to your pool, great, you can add disks online. They can be RAIDZ or Mirror or whatever, but once you do that, they're part of the pool. And kind of similarly with RAIDZ, let's say you start out, you add the right disks in the right configuration as a RAIDZ. It's a 6-wide RAIDZ1. If later on you want to add more storage, well, basically you probably need to add another 6 disks in another 6-wide RAIDZ1. You can't just add 1 disk at a time and make it now a 7-wide. Or can you? So I'm going to be talking about 2 new features that I've been working on in ZFS, device removal and RAIDZ expansion, which address those last 2 cases of disk flexibility. And we'll be talking about for each of these, we'll be talking about what they are, what problem is this solving exactly, and then a little bit of the implementation details, enough to help you understand how is this actually going to impact me when I run it. And then I'll be talking a bunch about the operational impact of I want to do device removal. What should I be thinking about? How's it going to impact my pool as I'm doing it, going forwards, et cetera? What should I think about before I do this, or how should I use it? And same for RAIDZ expansion. All right, so first, device removal. So what problems does this solve? So the first problem that it solves is over-provisioning. You add all this storage to your pool, and then you a couple months later you realize, oh, I actually didn't need all that space. This is one of the main reasons that we were thinking of it, that we motivated us to implement this at Delphix. How many people have had this problem? Oh, there's no hands up that I can see, because actually, it turns out people tend to fill up their storage. It doesn't matter how much storage you have, it's going to get filled up. Still theoretical problem that this solves. The next one is you add the wrong disk, or maybe the wrong configured the wrong way. So you have a bunch of disks attached, or you attach a disk through like a virtual machine, and then you realize, oh, whoops, I just added like the super slow disk, and I meant to add the fast one, and now the fast one is like slightly smaller, so now there's no way for me to do that. Or you add the wrong device type, like you meant to add it as a log device, but you add it as a main pool device. Oh, don't worry, I'm not going to ask for a show of hands of how many people have this problem. And then the last problem is one that really turned out to be the main use case at Delphix, which we call storage migration. So the idea is like you have a bunch of disks in your storage pool, and that's fine, and they're almost full because that's how pools always are. And then you want to add more storage, but it's been a couple years since you configured it. So really, what you want to do is switch to all new, bigger drives. And there's no easy way to do this with ZFS today, but device removal solves this problem really, really well. So like the example here is I have 10 1 terabyte drives, and I want to replace them with 4 6 terabyte drives, or maybe 5 or whatever. So this device removal works really, really well for that. So just from a high level, make sure everyone's on the same page. What we're talking about here is you have a storage pool. In this example, we have a storage pool which has 3 mirrors. Each mirror has 2 devices in it. And we're talking about removing one entire mirror and reducing the total amount of space in the storage pool. So this is in contrast with things like zpool detach, an existing command, which lets you take just one disk out of the mirror. In that case, you're changing the redundancy of the pool, but you're not changing how much like usable storage there is. Device removal, we're talking about changing the amount of usable storage. So to do that, we have to find all the allocated space on the disk that you're trying to remove and copy it to other places in the storage pool. All right, we're going to find all the allocated space. There's another operation on zpools that also needs to find all the allocated space that doesn't have a great reputation for being super high performance. Has anybody done a zpool scrub or replace? Well, I'm surprised that it isn't. Oh, it is all the hands. OK, great. Yeah, and as you might know, the performance of that is not wonderful. With device removal, we also need to find all the allocated space, but we're going to do it very differently. So we're going to do it using the space map. So in ZFS, there's a data structure called the space map. It keeps track of what space is allocated and what space is free. But that's all that it knows. So the cool thing is that it's very small. So you might have like one entry in the space map that says, this 100 megabytes is all allocated. That's just one entry. It takes like 8 bytes on disk. And there's obviously tons and tons of blocks, like logical blocks within that 100 megabytes. But we find it very quickly. And also, this data structure is sorted. So we can find all the allocated space very quickly and sequentially on the disk. So that means that when we're doing the device removal, we don't have to muck around with a lot of metadata. And we can read the data sequentially on disk. So we're going to get basically as good a performance as you could have for this copy. The one downside of this is that we aren't finding all the block pointers. That's the slow part. But the block pointers is where the checksums are. So we don't know what the checksums are when we are copying this data. I'll get to kind of the implications of that in a couple slides. All right, so I said that we're going to move all that data. But what about all the existing block pointers that point to the device that we're removing? Those still say, hey, like this part of this file is on device number 1, but that doesn't exist anymore because you removed it. So how do we find where we moved the data to? So we do this by keeping track of this mapping from the old offset and size to the new location, so the new disk and offset within that disk. And this mapping is sort of similar. Well, you can imagine that it's like sort of similar size to the space map. We'll get into some more details of that later. We always keep this mapping in memory. So like when you open the pool, we read it into memory. So we always have it there. So so everything's nice and fast. So wait a minute, did he just say that we're keeping this always in memory? How much memory are we talking about here? This is gonna, in the worst cases, this is gonna be pretty bad. As bad as like a gigabyte of memory per terabyte of disk that you have removed. And don't worry, this isn't like the common case. This is, at Delphix we work with databases, so we're using like record size 8K and compression, and everybody's always running their pools at full capacity. So this is on like a very fragmented pool. You would never see this bad if you're using like the default 128K record size, but we're not the only ones using ZFS with databases, so something to keep in mind. What do we do? What can we do to mitigate this? So we track what entries in this mapping become obsolete over time. So what that means is, let's say we move some chunk of data to somewhere else, and then we free the blocks that are in that moved chunk. Well, we keep track of, oh, actually, like I've freed everything in this chunk, so therefore I can actually remove the mapping, remove it from memory, and not have to keep track of that anymore. We added a new operation, ZFS remap, which will go and proactively try to find all the mappings through the block pointers, that's the slow part, but you have control over that and when it happens. And by doing ZFS remap, it allows us to obsolete entries in here much more quickly. But what if you don't want to worry about any of that? Well, I have a more than 10x improvement on this coming. So in that case, even in these really bad cases, we're talking about only about 100 megabytes of RAM per terabyte of disk, and much better for less fragmented pools. This is again an example on a very, very fragmented pool. So that's all cool. Everything's great. It all works. I just wanted to give you a little bit of look into two aspects of this that are a little tricky. What I said so far is kind of like, yeah, you just find the blocks, you copy them, done. We have a mapping. It tells you where to get the data. It's a little bit more complicated than that under the hood. So remember, we're doing this while any other operations are going on. You could be reading and writing data. You could be freeing data. We disable allocations on the device that's being removed, since there's no point in letting you allocate more stuff there, since we're just trying to move it somewhere else anyways. But you can still, you still might need to free stuff that's on that device that we're removing. And that's a little bit tricky to handle when we're in the middle of removing the disk, right? Because remember, removing the disk, step one, find all the allocated space. Well, I'm changing the allocated space while you're doing that. So how does that work? There's three cases we have to worry about. The easy one is we haven't copied it yet. OK, great. Just free it from the old location, same as we always have done. What if we've already copied it? Well, in that case, there's two copies of the data, one in the old location on the disk that we're removing, and one in the new location on one of the other disks in the pool. In that case, we need to free it from both the old and the new locations. But what if we're in the middle of copying this particular block? So we've issued the reads from the old location, we got the data, now I've issued the write to the new location. Well, if I consider it not yet copied, then, well, I already allocated the new place, so that's not going to work. If I consider it already copied, and I free it from the new location, then I'll have freed the right thing while I'm in the middle of writing it. So if somebody else allocates that after I've freed it, then they're going to overwrite the thing that I'm trying to write. Or I'm going to overwrite the thing they're trying to write. So if we're in the middle of copying it, then that's a really tricky special case, and we have to remember we free it from the old location and the new location, but we have to wait till the end of the transaction group when the copy completes to actually do the free. OK. One other tricky thing I wanted to mention. So I said the space map tells us where all the allocated space is. It might say this 100 megabytes is all allocated. There's a whole bunch of blocks inside that, but we don't know where those blocks are. We don't know where the boundaries between those blocks are. We just know that there's 100 megs of data here. I got to find somewhere else to put it. We might not be able to allocate 100 megs of space contiguously on somewhere else in the pool. So we need to split this region into two or more segments. And part of this contiguous region goes to one location, and part of that goes to a new location. The annoying thing about this is that this split might be in the middle of one logical block. So now maybe like this is one logical block, this is another logical block, and then this part is the third logical block in this contiguously allocated region. So when I read this logical block, I have to read the first part of it from here and the last part of it from here. So that's not too hard. But it has some more interesting implications that I'll show you in a few slides. So keep that in mind. So there is one big caveat to this, which is that it does not work with RAIDZ. So it does work with plain disks and mirrors. RAIDZ is a little tricky. There's some areas of future work here that I'll mention at the end. There's also one small caveat, which is that the devices have to all have the same A shift. That would typically be the case, so it's not really operationally much of a constraint. OK, so on to how do I do this? Like, what do I type? You've convinced me that this is super cool and I should do it. What do I type? So first thing that you want to do is check how much memory will be used after the removal completes. Since this might be a really big number that might make you rethink if you really want to do the removal. Although, like I said, improvement's coming. So you do zpool remove -n means dry run or no op. The name of the pool, and then the name of the disk that you want to remove. And this could be like a literal disk like this, or if we had mirrors, then it would be like mirror-0 or mirror-1, where the last number is the VDEV ID, which shows up when you do like zpool status. And that'll tell you, OK, if we remove this, I predict that it's going to use about 50 megabytes of memory. Great, we say that like got plenty of memory to do that. You run zpool remove, name of the pool, name of the disk. That goes off in the background. You can be doing whatever else at the same time. You check the status of zpool status. And now we have this new line here telling you that we're in the middle of removal. And it's kind of similar information to a scrub. It tells you like when it was started, how much we've done, how much there is to do, the rate, and an estimate of how much longer it's going to take. While we're in the middle of the removal, you can cancel it if you need to. So like, let's say you forgot to do the first step of checking how much memory there was, and then in the middle of the removal, you're like, oh, wait, how much memory is this going to use? Well, you can cancel it if you need to, or if you realize you made a mistake for some other reason, or you realize that, oh, this copy is like taking longer than my outage window or my like window where I can have degraded performance. So I'm going to go ahead and cancel that. We basically just have to go free all the new locations of the data to implement that. Also during the removal, what if we like lose power or reboot? That works fine. It's going to pick up where it left off, kind of similar to the way scrubs work. What if you want to do something else during the removal? Everything pretty much works. Like you can add devices, you can kick off a scrub, you can change properties, create file systems, of course. This slide formatting didn't quite come out right. There's supposed to be an asterisk. Everything except for a new upcoming feature, zpool checkpoint, which lets you take kind of like a pool-wide snapshot of everything in the whole pool. That doesn't work with device removal because like after the device is removed, then you can't like the data isn't there anymore, so the checkpoint wouldn't work. But aside from that, basically like it all works with everything else. After the removal completes, the zpool status is going to tell you about that. It's going to tell you, kind of similar to a scrub again, you removed a VDEV. We did this much work. It took this long. And then also how much memory is used. And this memory used for removed device mappings is for all device removals that you've ever done. So this status is just for the most recent one, kind of similar to a scrub. But this memory used is, you can remove more devices over time. So That's the total sum, and that will also reflect like the like remap stuff and things becoming obsolete. This will reduce over time. Okay, so I wanted to talk a little bit about performance impact. There's kind of two aspects of performance that we need to think about here. One is performance during the removal, and the other is performance impact after the removal has completed. So during the removal, like I said, we got to copy all the data. So this is not going to be an instantaneous kind of operation. But the reads are sequential, so that's very good. It's going to be a lot better than scrubbing all the data, for example. We didn't really work that hard at making this go fast, I'll admit. We were more concerned with having it not impact the performance of the rest of the pool too much while it's going on. So there's this tunable that controls the VDEV queue, and it sets the maximum number of IOs that will issue to disk as for the removal at once is 2. So in other words, like we're only going to send 2 IOs to the disk at a time, and those 2 IOs are going to compete with like the other IOs, like reads from the disk that are normally going on, which have a much higher default queue depth limit. I think the default is 10. And the time that it's going to take is proportional to the amount of space that we're moving, but also to the fragmentation in the pool, since like we're allocating space in the rest of the devices. If there's tons of contiguous free space, then we're going to be doing contiguous writes. If the free space is super fragmented, then those writes are going to go to lots of different places, just like writes to the pool normally do. After the removal completes, what's the performance impact? So we talked about the memory use. Again, you can check that with z equals status. The other impact is pretty negligible. There are a bunch of things that we have to do on an ongoing basis with after you've removed the device, but the performance impact of them is really not noticeable. I will just mention them here so that you can understand what we have to do. So one, I already mentioned, when we open the pool, we have to read in the mappings. Those are stored super contiguously in files with objects with big record size. So this is typically a pretty small number of IOs. Whenever you do a read, we have to look up in that mapping to find where the new location is, right? Assuming that the read is coming in to the removed VDEV and it hasn't been remapped. So that's O of log n, where n is the number of entries in the mapping table. The mapping is also stored contiguously in memory, so we just like allocate a big chunk of memory. It has the entries stored super compactly, and we're doing a binary search on that. And then we have to track the obsolete mappings. So this is kind of similar to, if you're familiar at all with how snapshots work. And by the way, I have a whole other talk that's about how space maps work. You can find a video of that online. I also have a whole other talk about, actually it may not be, yeah, I have a whole other talk about how snapshots work and how we keep track of like the space that's free in snapshots. The obsolete mappings work kind of similarly to that, because we need to keep track of like, is this part of the removed VDEV referenced by any file systems, and is it referenced by any snapshots? So when we don't reference it from the file system anymore, say you did like a ZFS remap operation, then the file system won't reference it anymore, but there might still be snapshots that do refer to that segment of the removed VDEV. We need to keep track of that and then know like when I've deleted all the snapshots that refer to it, then I can get rid of that part of the mapping. So we needed to keep track of all that. The performance impact is kind of similar to keeping track of that kind of thing for snapshots, like to keep track of when can I free this data when I delete a snapshot. This is probably the biggest of these minor performance impacts, but it's still pretty minor. People usually don't notice the performance overhead of keeping track of that stuff for snapshots. They notice like when I delete a snapshot, how long does that take? But we don't really have that use case here. Okay, so lastly, I wanted to mention what's the impact on redundancy, right? Like let's say you have mirrors and you're removing one whole mirror. Like, does that work? Like, what's the impact? So it does work. We preserve all the copies of the data. So what that means is that, which I kind of tried to show in this diagram that I threw up earlier, what that means is that we actually read both copies. So we read from like the left side of the mirror, and then we write that data to the left side of the new location. And I read from the right side of the mirror and write that data to the right side of the new location. So if there was any silent damage, if there's any silent damage to one side of the mirror, that damage is preserved. So you're in the same situation as you originally had, where like if I had one side is damaged and one side is good, after I copy it, I'll still have one side is damaged, one side is good. And when we read from that location, when we do have the checksum, or if you do a scrub, then we're able to detect and correct and repair that, that damage. And that applies even for split blocks, which is like kind of a nightmare to implement, because you could imagine like if I have a split block where half of my logical block is here on this mirror and half of my logical block is on this other mirror, then when I read it, I don't really know. I read it and I get a checksum error. I don't really know like which part of it is wrong. And the normal algorithm is to assume like, well, one of the two sides of the mirror that I read from must be wrong. So let's pretend that the left side is the right version. Does that give me the right data? Let's pretend that the right side of the mirror is the right version. Does that give me the right data? But here there's two mirrors involved. And so we need to implement a bunch of special logic to try like all possible combinations. Because it might be that like the left side of this mirror is damaged and the right side of this other mirror is damaged. So I need to figure that out and use like the right side of this and the left side of that and combine those together. And you can actually have blocks that are split into more than two sections, right? It could be split into like an arbitrary number of sections. So we have to try like all the different combinations. Okay, I think I'm still on track despite these diversions. As I mentioned before, however, the checksums are not verified when we're doing this. So the impact of that, operationally, is that transient errors will become permanent. In other words, like if I read, I read from both sides, if this read gives me the wrong data, I'm writing that wrong data to here. And I don't know that, right? Like as part of the device removal migration, I'm just copying whatever the read gave me. And if you have something like, these transient errors typically don't occur on, like, you don't see these a lot on spinning disks, but you do see them more on things that have more software in them, because these transient errors tend to be caused by software problems, not by hardware problems. Like the hardware is like, I already have like a zillion bits of ECC down here, and like when you do the read, I'm trying all of them, and like I'm already reconstructing like all kinds of crazy stuff. I'm giving you the best that I have. But if it's an SSD or if it's like a some fancy storage box, storage array, hardware RAID, going over fiber channel or anything like that, there's a lot of software involved, and software can have race conditions and caches and a bunch of other stuff. So that's where it's possible to see these transient errors. I would say it's not common, but it is something to be aware of. In the case we're using mirrors, of course, hopefully there's only a transient error on one side of the mirror and the other side is good. And so next time you do a read or a scrub, it's going to correct that. So what's the status of this? Can I use it? First, I want to thank a bunch of folks, other developers who helped implement this. Alex, Seraphim, Prashanth, Brian, and Tim. We've been using this in production at Delphix for a long time, since 2015. It took us quite a while to implement all the features that I mentioned here and then get around to upstreaming it. So we just integrated into Illumos in January and in ZFS on Linux just a couple weeks ago. It'll be in 0.8. In terms of next steps, the mapping, this map big chunks thing that I alluded to, that'll reduce the space reduce the memory usage by about 10x on super fragmented pools. That's out for review now. We're hoping that'll also get into 0.8 of ZOL. Cool. So questions. We're going to move on to RAIDZ expansion next, but I think we probably have time to take questions that are specific to device removal now, at least a couple questions, if there are any. Yeah, go ahead.
Does it add a new feature flag?
The question is there a new feature flag? Yes, definitely. So all that stuff that I said we have to do, where did I say? Like, read the mapping when the pool is opened and look up in the mapping. Old software doesn't know how to do that. So yeah, there's a new feature flag. It's not backwards compatible. Like once you do this, you can't take it back to an old pool, even read only, right? Because it doesn't know how to do these reads. Yeah.
So the removal layout class, is it now the lowest priority?
Yeah. So the question was the I/O priority. Yeah. So there's a new queue for the removal I/Os, and those are the lowest priority. Yeah.
So you mentioned it's not it's only for mirrors and single display. It's not for latency.
Yeah.
Is that coming at some point, or are there technical challenges?
I'm going to defer your question until my very last slide. Yes.
Say you do this and you're okay with the memory usage, then at some point in the future your workload changes and you need that memory back. Is there a way to go through the block pointer tree and free all of it?
So the question, yeah. So the question was, what if you need that? What if you did the device removal and it's using that memory, and then you're like, I really don't want to do that. Is there any mitigation? So you can run ZFS remap, which I realized I should have included a little bit more about in these slides. So you run ZFS remap and then the name of the file system. It'll go through and find all the block pointers in that file system and try to replace them with block pointers that refer to the what we call the concrete location, or the one that is the new location. And we can't do this for all block pointers. So for example, split blocks, there's no like one new location that we can represent in a block pointer. So those wouldn't be able to be remapped. But any other, any non-split blocks, we can do that. Then the only remaining thing would be snapshots. So if you were in this situation, the way out of it would be to run ZFS remap on all of your file systems and all of your clones and all your ZVols, and then age out or delete all of the old snapshots from those. And then you should see the space used. Probably not going to take too long. The memory used here is going to go down a lot as a result of that. And at Delphix, we do that in part because like the map big chunks thing, like that's not even in Delphix. So and our customers are generally like they're using 8K record size in compression and full and like super fragmented. It's a really nasty use case. It's really challenging use case, I should say, for both for ZFS and for device removal. So we put in a bunch of work to make this like be usable. And like one of the things that we do is we have a lot of file systems, but we have more snapshots and also a lot of clones. So what we do is we go and do, after the removal completes, we do a remap on all the file systems, the non-clone file systems. And then over time, as customers' snapshots age out and they refresh their clones, meaning like they destroy that clone and they create a new clone from the more recent snapshot, then it's going to cause that memory usage to decrease. And we've seen that happen in practice, although obviously it's very dependent on the customer's retention policy for their snapshots. Okay, maybe if there's one more question, I'll take it now. Okay, cool. Then we will move on to RAIDZ expansion. And I'm only a little bit behind schedule. Am I going to get yanked off stage? Okay, good. So RAIDZ expansion. what problem is, the problem here is a lot simpler. You have a RAIDZ pool, and you have 4 disks in it, and you want to add a 5th disk. Has anybody had this problem? More people than I expected. Awesome. So I'll spoil it a little bit by saying the problem is not solved in the past tense. I am working on solving it. And I'll be talking about what you will be able to do in the future once this is fully implemented. So like all that we have to do is just rewrite everything with a new physical stripe width. And then that'll increase the total usable space. And we won't change the relationship of the data and parity. Everything will just be preserved. Great, OK. Talk done. See you guys. It is quite a bit more complicated than that. Let's start by thinking about how traditional RAID, like RAID 4, 5, 6 works. And then I'll kind of explain the difference of RAIDZ, because in case folks aren't familiar with, like, even aside from RAIDZ expansion, RAIDZ is pretty different than this. So in traditional RAID, the parity is at fixed locations on disk. Here I'm showing RAID 4, but like RAID 5 is basically the same thing, except for that the parity rotates diagonally. And with RAID 6, it's like there's more parity in there. So like this physical row, like offset 1 of all of these disks, is also the logical row, meaning that this is the parity of these 3 blocks. And that's true like regardless of what data is stored there, what the file system knows about. It's just like, if you're writing to block 7, then great, like the parity is here, it's 2 blocks later, and I'm going to like read the old data, XOR it into this thing, and then write out the new parity. And like there's a bunch of problems with that, like the RAID 5 write hole, that we're not going to worry about for right now. So that's how traditional RAID works. How could it do expansion? Well, we just like increase the width of this, and kind of like if you're using a text editor, like if you're using Microsoft Word and you increase you decrease the margins, then it reflows your text to go wider. So we just number the sectors on disk differently. Instead of 1, 2, 3, 4, 5, 6, we say 1, 2, 3, 4, 5, 6, 7, 8. And we move the parity here. So the parity, instead of this parity for the first row being the parity of 1, 2, 3, now it's the parity of 1, 2, 3, 4. So obviously we have to like recalculate all of the parity to do this. But this it at least looks straightforward. With RAIDZ, it's a little different. It doesn't look as straightforward, but I'll explain why it's actually simpler than in the traditional case. So with RAIDZ, we solved the RAID 5 write hole by saying that there are no partial stripe writes. And the way that we did that was by saying the block that includes, like the logical block allocation includes the parity for that block. So in this case, let's say that the first logical block is 4 sectors long. In that case, we would have its sectors like 2, 3, 4, and 6. The first row here has the parity here of 2, 3, 4. And then the second has the parity just of 6. So in this case, it's kind of degenerate because the parity is just of a single sector. But the impact of this is that like you might have a little bit more parity on RAIDZ because like, see in this like physical row, we have 2 parity blocks rather than just the 1 that you would have in the, that you could only ever have 1 in a traditional case. Solving the RAID 5 write hole is obviously like a big deal, and doing so without having to require special hardware or having performance implications is really great, which is why we implemented RAIDZ. This is all background information on RAIDZ. How do we do expansion? Well, it's kind of similar to what we saw for the traditional case, but instead of reflowing just the data and keeping the parity at the same locations, we're reflowing everything, the data and the parity, which is kind of just the natural thing to do because in RAIDZ, like we're allocating the parity is at fixed locations. It's just like part of the block. Like when the DMU has a block pointer, it just says like I have like the first block is just a logical block from 1 to 6. It doesn't really know where the parity is. It doesn't care where the parity is. The RAIDZ code knows about that, and it worries about it when it needs to do reconstructions. But like the allocation code doesn't care about that. The DMU doesn't care about that. So we can reflow this without regard for where the parity is. So the first physical row is now, instead of 1, 2, 3, 4, it's 1, 2, 3, 4, 5. And it doesn't really matter that the parity is here for this block. So this works because all of the, so the reason that RAID works in general, RAIDZ or traditional RAID, is that for any logical stripe, the data, each sector of data and each sector of parity are all on different disks, right? So like here, this logical stripe of 7, 8, 9, 10, 7 is the parity of 8, 9, 10, are all on different physical disks. So if I lose any one physical disk, I'm only losing at most one sector of each logical stripe. When I do the reflow, that property is maintained, and that's what makes this work. So because it's getting wider, like it's only getting better in terms of like the number of sectors of each row that could be damaged when one disk dies. So like if this disk were to die, we lose one sector out of this first pink row, one sector out of this beige row, no sectors out of this yellow row, one out of this green, and one out of the blue. So obviously, we cannot do RAIDZ contraction using this same kind of mechanism, because then you'd end up necessarily with like multiple sectors of one logical stripe shared on the same same device. Since obviously this is ZFS, we know where the allocated and free data is. So we'll find the allocated data, and then we'll reflow it according to this new, essentially it's like a new numbering scheme or addressing scheme for this RAIDZ device. So like if this white part is not actually allocated, we don't copy that data. So step 1, find the allocated space. We'll find the allocated space using the space map, not using the block pointer. We find the data, like there's very little data to find, very little metadata to traverse to find that what's allocated and what's free, and we find it sequentially. So our reads in this case and our writes are necessarily sequential, but we have no checksum verification. So hopefully this looks a little familiar to the previous section of the talk, and some of the implications are similar here as well. So I think I kind of mentioned this. Each logical stripe is independent. That's how this works. Cool. So how will this work? What do I type to do it? So we'll initiate the expansion with zpool attach. Zpool attach is an existing subcommand that's used to attach disks to mirrors. So like if you have a 2-way mirror and you want to make it a 3-way mirror, you can use zpool attach and then like mirror -0. Or if you have a single device and you want to turn it into a mirror, you can do like zpool attach, the name of the old device and then the name of the new device you're adding. So I've extended that so that now you can attach to a RAIDZ. So you do zpool attach, name of the pool, name of the RAIDZ vdev, which is RAIDZ1, meaning you have one parity in here, and then dash and then the vdev ID, which you see from zpool status, and then the new device that you want to attach there. So this works with RAIDZ 1, 2, and 3. You can expand it multiple times. It will work in the background and display status with zpool status, kind of similarly with scrub or device removal. That is not implemented yet, so I'm not showing an example of it. One kind of interesting caveat here is that the RAIDZ needs to be healthy during the reflow. So what do I mean by healthy? So silent damage is still okay, up to the parity limit, just like normal. Like, if you have RAIDZ 3, like you can have any 3 sectors of your stripe be silently damaged and ZFS doesn't know about it, but like that's fine. We're gonna we're just gonna copy whatever data is there to the new locations. And so you'll be in the same situation where you have like three damaged sectors of that stripe, and we'll be able to reconstruct it. But what I mean by being healthy is that we have to be able to write to all of the drives. If there's some drive that you can't write to, then the reflow can't proceed, and so we'll just pause the reflow when we detect that, and then resume it when the missing device comes back. Yeah, so just dies reflow. Yeah, cool. So what are the performance impacts? Again, we're going to talk about during the reflow versus after it, because there are implications once it's done. So during the reflow, like we're copying all the data. So that takes time. It's not going to be instantaneous. But the reads and the writes are all sequential. Since like the writes are, we're not allocating new space for the writes like we are with device removal. We're just writing it to new like known locations. It's all going sequentially. After the reflow, there is going to be some minor impacts. So I would say these are not major, and I wouldn't worry about these when considering using this. But to make you aware of what's going on, when we're reading the data, there is a small CPU overhead. Basically, we have to copy the data in memory one more time to get it all sequential. With RAIDZ, let me see if I can go back all the way. I think we have enough time to show you this. All right, so so with the actual layout of your data in RAIDZ is really complicated. I know you're thinking like, what, like this wasn't complicated enough already? But keep in mind, like here, each color is showing a logical stripe. But one logical block is composed of multiple logical stripes. So for example, like maybe these last two stripes, the blue and purple, are actually one block. So like the block is 6 sectors of data, and we allocated this, these 8 sectors to store it, including this 2 parity. The way that the data is actually written is the first part of your data is here, and then the next part is here, not here. So it's like within that logical block, it's thinking about it as data sector 1, 2, 3, 4, 5, 6. And the reason that we do that is so that when I do a read from this disk, I can read all of the data for this disk into one contiguous chunk of memory, and then all of this, and then all of this. So like when I issue those reads from disk, it's like I have to do 3 reads from disk from each, one from each of these 3 disks. But I only have to do 1 read to get it into the right place in memory to have it all sequential to give back to the consumer. In the new world, like that's not the case, right? Because I said it's 14, 18, 15, 19, right? But now it's like 14 and then 18 and then 15 and then 19. So I kind of had 2 choices. One is like, well, I didn't really, but one is I could have said, let's issue reads for each individual sector. So I'll arrange it in memory so that like 14 goes into the first location in memory. Then I issue the read for 18, the second location, 15 for the third location, et cetera. So I just do the reads from disk, and then they come back into the right locations. But that means that I've done many, many more reads from disk. And so the performance is going to be like way worse because the typical case is like you have some big block, and it composes lots and lots and lots of rows. You have like if you even with like even with only the default of 128K blocks and 4K sectors, those are still comprise I forget, like a dozen rows or something. So multiplying your number of reads by a dozen is not good. What we do is we issue a read from this disk for all of the data that we need for this block, and then we like move it around in memory to get it all sequentialized. And the reason I said that I didn't really have that choice is because the cool thing is at the RAIDZ layer, I actually do issue all these reads, but there's a layer below it, the ZFS Queueing layer that does aggregation, and so that just detects like, oh, you issued like a whole bunch of one sector IOs that are actually sequential. Great, I'm just going to issue one read from disk, and then like bcopy it all back to the buffers that you gave me. So like at the RAIDZ layer, I'm actually saying like, oh, I do issue a zillion little reads and tell it to put it into the first, second, third, fourth part of the memory buffer that I need to go to. But the layer below me takes care of all the issuing one big read and then bcopying it and whatnot. The reason that that's that we want to do it that way is because like you might IO aggregation code is beneficial in the normal case, even ignoring RAIDZ expansion, because like you might be reading a whole, like you might have written a file to disk all sequentially, and then you're reading it sequentially, and so we need to read not just this block, but also the previous and next blocks, because prefetch is there, issuing those out in advance, and so then you can get much, much larger reads from each disk. Otherwise, like consider the case of like 128K blocks, 4 wide, if you didn't have this aggregation, in the best case, you'd be issuing 32K reads from disk. But with the aggregation, it can go all the way up to the aggregation limit, which is at least 128K. OK, I'm not too far behind. During reflow, right? OK, I was mentioning this. OK, so one, that was a long diversion. Thanks for sticking with me. The other performance impact is to combinatorial reconstruction. Does anybody, so RAIDZ does this today. Does anybody know what this is? One hand a quarter of the way up. OK. So I talked a little bit about how ZFS repairs silent damage. So silent damage, what I mean is like the disk gave us the wrong data, and ZFS didn't tell us that it was giving us the wrong data, right? The opposite of this would be like the disk fails, and then it tells us, hey, I don't exist anymore. Your IOs don't work. And then ZFS says, OK, that's great. I know that you don't work anymore. I won't ask you to do anything. I'm going to reconstruct your data from this other side of the mirror or the other RAIDZ devices. I know what to do. The silent damage is where ZFS doesn't know what to do a priori. We read from the disk says, here's your data, and then we say, actually, that's not my data. I performed the checksum, and that is definitely not what I wrote. And now I need to figure out, like, how do I find the right data? So in RAIDZ, just go back to this slide. I should have just had a million copies of this, this one slide. So let's ignore reflow for the moment. With RAIDZ, like let's say we read this block, which is these 2 rows, and checksum is wrong. All right, well, I guess we read these because we started out, we don't need the parity to read it. We read this, we say checksum's wrong. OK, well, I don't know, like probably one of these disks gave me the wrong data, and so I should reconstruct that disk's data from the parity, but I don't know which disk went bad. So I have to try each of them. So I say, let's pretend that this disk is bad and reconstruct its data from the parity, and then perform the checksum. Did that work? Nope, still have the wrong data. All right, what if this disk's data was bad? Let's pretend it's bad, reconstruct its data from the parity. Does that give me the right data? Oh, the checksum is correct. Great. So therefore, I know that you lied to me. I read the data. You said that you had it. That was not the data that I wrote. So I can, there's a bunch of like fault management stuff that can happen under the hood to say, oh, this disk might be wrong, might be going bad or whatever, but at least I got the right data and I can give it back to the user. That was kind of simple, but imagine like RAIDZ 3, where you can have 3 dead disks and need to reconstruct it. You might have like a 20 wide RAIDZ 3. We do try the simple cases first, like hopefully only one disk is dead. So let's try, try just reconstructing from one, assuming one of those is dead. But it might be that like 3 of those disks gave us the wrong data, and we need to be able to reconstruct it. So the goal here is like, you can take any disk and like, you can take any 3 disks in RAIDZ 3 and B0 them and not tell ZFS, and we'll figure out what to do. Every read we'll go and try like, okay, which combination of correct data and wrong data can I reconstruct to get the right answer? So in terms of math, that's like it's called a combination. So we need to try all the combinations, and it's like the width choose number of choose like the number of parity disks. So like this would be 4 choose 1 there's 3 combinations. This one, or this one is dead. But if it's like 20 choose 3, that's like exponential in I think both the parity and the width. So all right, so I said, I gotta go back to the other side. So I said that we want to be able to handle, I'm gonna go over, but I find this stuff really fascinating. I hope that you guys will bear with me. I said we want to be able to handle, like with RAIDZ 3, you can B0 any 3 disks and everything's fine. So what if I say, great, I'm gonna take you up on that. I'm gonna B0 one of the disks, not tell you about it. Then I'm gonna do a RAIDZ expansion. Then I'm going to B0 another disk. Then I'm going to do another RAIDZ expansion. And then finally, I'm going to B0 a 3rd disk. Well, from the point of view of like where the damaged data is, it's not just all one disk, right? So like this logical block, in this simple example, let's just say that we damaged one disk and then we did the expansion. That'll be easier to understand. So let's say like we damaged this disk, and so 14 and 18 are damaged. And remember, like this is one logical block, so we have the checksum of this logical block. I don't have the checksum of each row individually. I just have the checksum of the whole logical block, all 6 of these sectors. So before the expansion, I silently damaged 14 and 18. And so if I did the reconstruction now, we would say like, oh, try this one doesn't exist. OK, great. We can reconstruct the data. But after the expansion, it's 14 and 18 that are damaged. So there's no, like I read this one logical block, and then I say, great, like the checksum's wrong. Let's try reconstructing it. What if this disk is bad? 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 Oh, they all gave me the wrong checksum. Because like when I assume this one, well, OK, that was not a great example. If I assume this one is dead, then I'm going to reconstruct 14, which is great, because that's the one that is actually wrong. But then I'm going to reconstruct 19 and leave the bad 18 data in there. So I'm not going to get the right checksum. So that's why, in addition to trying each of these disks being dead, I need to try what if each of the previous incarnations of disks are dead. So like, what if child 3, when I was 4 wide, is dead? Or in this case, it's child, I guess we start from 0. I should have started from 0, but let's call this one child 2. What if child 2 was dead when it was 4 wide? OK, so in addition to trying these 5 times, I also need to try what is essentially kind of like, think of it diagonally, right? Like these 4 times. So then I'll try, for this block, I'll try, what if 13 and 17 are dead? Well, those are with parity, doesn't matter. What if 14 and 18 are dead? Aha, those are the wrong blocks. So now I can reconstruct. So you might be saying like, OK, I get it. There's multiple rows here, and I only have the checksum of the entire block, which is multiple rows. Why don't you just try, like, why don't we just always try like every possible combination of sectors? Because it's a zillion. Like, literally, you could start the reconstruction of one block, like one 128K block now. You could start that now. Like, it will not complete before that computer fails. So we can't try all of them, which is why we can't try all of them in this case either, which is why we continue to make the guarantee that like if any if any P disks are silently failed, then we can reconstruct it. And we're saying that's true at any point in the lifetime of the RAIDZ. So if it failed in the past, we'll still be able to reconstruct it. But like, if you just come and shoot like this sector and this sector, like we're not going to reconstruct it. Sorry. And that's true for like mirrors and stuff too. We talked about like mirrors and split blocks and how we have to do crazy reconstruction there too. But the caveat, so I talked about zeroing out whole disks and how we handle that. A more kind of special case of that is what we want to handle is like we can have P errors on any, you know, if you have RAIDZ 3, you can have 3 errors on any in your RAIDZ as long as they're sufficient, as long as those 3 errors are sufficiently spatially distributed from a different set of 3 errors. So, you know, if this one is wrong, that hasn't like used up like, oh, that only that one can never be wrong for this whole RAIDZ. Like you could have these ones wrong and these ones wrong, and we can reconstruct that because they're part of different physical, different logical blocks. So we have different checksums for them. But it doesn't go arbitrarily far. Okay. Maybe I went a little bit too far with that explanation. Great. Okay. Redundancy impact of doing this. This should also look familiar. It preserves the data in the parity, but we don't verify the checksums, so transient errors will become permanent. Luckily, with RAIDZ, like at least you can at least survive one error. Oh, the other interesting aspect of this is what's the impact on space usage? Obviously, you're adding new storage. You're going to have more free space now. The free space is all kind of like at the end of the disks. So the free space is like logically contiguous, which is great. And otherwise, the space usage is unchanged, which means like the data to parity ratio is the same as it was before. So like here, you have 1 parity for every 3 data. After the expansion, all that existing data still has 1 data for every, one parity for every 3 data, even though you're 5 wide. But new writes will use the new logic, the new stripe width. So you'll get the new data to parity ratio. So like if we write this new green block, then we'll only have 1 parity for the 4 data blocks. Cool. So status, first of all, thanks to the FreeBSD Foundation, they're sponsoring this work. The design is complete. I have a pre-alpha, I'm calling it a pre-alpha preview code. So don't use this. Oh, another thing didn't quite come out on my slide. This is supposed to be like in bright red. You will lose data if you use this. If not because of an error that I made, because of like the on-disk format is going to change. Like there's not going to be any compatibility across versions or being able to bring this to the final, bring your pool to the final version. Like no, none of that. This is way too early. I'm doing the reflow all in one TXG. So like you run the, you type zpool attach, and then like everything halts. No writes. I guess reads will still work. But like we're not accepting any more data into the pool. We're just sitting there in that one TXG for like an hour or however long it takes to do the reconstruction. But when it's done, you have more space. You can read all those old blocks. It can do reconstructions. So like a lot of the fundamental stuff here that I've talked about is all working. If you're interested, the code is up in a code review here. I can put it up on GitHub if that's more convenient for folks. And I'm going to be giving a talk, a whole talk just about RAIDZ expansion at BSDCan in June. Cool. So, all right, I promise. Oh, this is not the last slide, but almost last slide. I will answer the previous question about future work. So I mentioned on device removal, mapping big chunks, huge improvement in the worst case of memory usage. The review is out now. We hope to get it into ZFS ZOL 0.8. Another cool improvement that we'd like to do to device removal is, for the example that I gave, which is what a lot of our customers do, they're like, I want to remove, I have 7 devices. I'm going to add 5 new devices, and then I want to remove all 7 of those old devices. Well, the way it works now is you remove the first one, and it's allocating space on the rest of the pool, including the 6 old, probably slower, and definitely much more fragmented devices that you're just trying to remove anyways. So we'd like to be able to queue up multiple devices to be removed, and what that would mean is we would just mark those as, hey, don't allocate from these devices that are already queued up for removal, and it'll also make it easier to check if you have enough memory for all of them to be removed, and check that you have enough space that you have for all of them to be removed. We have a prototype of this, but it needs a bunch of work. I don't really have an ETA on that. If somebody wants to work with us on that, we'd love to mentor you. But this is kind of where we see the next thing to do for device removal. Aside from that, it's pretty well baked. All right. So this is the question that you're asking. What about removing RAIDZ? This is possible. It fits very well with the existing design, especially when you combine it with RAIDZ expansion, because then you could do this if the other VDEVs are equal or greater width. So without RAIDZ expansion, you could do this if all the VDEVs are the exact same width. So you have 3 VDEVs, 3 RAIDZ VDEVs. And all 3 of them are RAIDZ 1 5 wide. Then you could remove one of them. There's some additional work that we need to do to make that happen, but it would be kind of a logical extension. But then if we also have RAIDZ expansion lets us handle the case where the logical and physical stripe widths are different. So in that case, we would be able to do a RAIDZ removal where the remaining devices are of greater width. And potentially even different amounts of parity. So it's a little tricky to do. So, the device, well, I'll let somebody ask the question if they want to hear more about that, because we're already over time. Last slide, I wanted to announce the OpenZFS Developer Summit is, we are going to have, again this year, 6th year running. It's going to be the week of September 10th, either the Monday, Tuesday, or Tuesday, Wednesday of that week. We're still finalizing the venue. And we're looking for talks again this year, as always. We had some great lineups in previous years, and I'm always amazed that the talks keep getting better every year. So please don't let me down. Talk proposals are due in mid-July. And with that, questions about RAIDZ expansion or device removal or anything else? I'll go as long as until they kick me out. Yes.
Yes, I had a question on the RAIDZ. Maybe it's implied, but you mentioned silent data corruption or silent errors become basically more checksums aren't verified and transient issues become permanent. Will that remain when this is actually production ready?
Yeah. So the question was about the transient errors becoming permanent, and yeah, the plan is that will remain in the final version of this, as it is with device removal.
So you mentioned in passing that as long as it's underneath your parity, accurate protection, you're okay.
Yeah.
But ZFS will not know if you violate your parity when that happens, correct?
Oh, it will. When you do the read, so when you.
At some point in the future.
Yeah.
Like a scrub runs, then you will find
Exactly.
out I've actually lost data, but not during that.
Yes. So it's still ZFS. We're still we're still never giving bad data to users. we're verifying the checksums when the user reads the data or when you do a scrub. So
is there a reason not to verify checksums when you're doing the reflow just to make sure, but just to catch those issues?
Performance is a big reason. So the question was, why don't you verify the checksums? And the answer is performance. So it could be done. I mean, and that could be an extension of this where you say, hey, I'd like to actually I want to go through all the block pointers, find all of the logical blocks and get all their checksums and sort them and then do the reads. For RAIDZ expansion, that's especially challenging because we have to do the reads sequentially. Like we have to do the reflow sequentially. You can't just reflow as we find the block pointers because then we might be the new location of that block might be somewhere that we haven't reflowed yet. So it still has some old data on it that we need. So in order to make that work, you'd have to, assuming that you don't have unlimited memory, you'd have to do multiple passes over reading the metadata to find all the block pointers, where you're saying okay, first I'm gonna read all the metadata and find, I'm gonna use a gig of RAM and I'm gonna find that, that covers whatever, 1 million block pointers. And so I'm gonna find the first 1 million block pointers. Okay, I've been told that I only have 5 more minutes. Yeah, so performance, if you're okay with this performing like a scrub, then it's totally doable. There'd be some work to implement it, but I chose to make the trade-off both with device removal and RAIDZ expansion that it was that one reliability caveat was worth it for the huge performance wins. Yeah. Another thing, if you're super paranoid, you could run a scrub before you do the RAIDZ expansion or device removal for that matter. If it turns up any errors at all, then maybe it makes you suspect I wonder if those were transient. Let me try it again, or makes you into even more paranoid mode before you do this. More questions? Yes.
Does device removal and RAIDZ expansion generate Zen events like scrubs do?
The question was, do both of these generate events that go into Z, for example? Yeah, they do. It turns out both of these are just they're just more general cases of existing functionality in ZFS. So you can already remove devices in ZFS, just caveat only log and cache devices. And we generate events for those, and the same event will be generated for this kind of device removal. And same with attach. You can already attach devices, caveat only mirrors. So now it'll generate that same event for RAIDZ attach. More, oh yes.
When you do RAIDZ expansion, then you have to remember forever how many times you've expanded so that when you need to do the reflow or when you need to recalculate,
Yep.
you know how diagonal to make it.
Yep.
But if you have multiple cases where you added, like you said, added,
Mhm.
corrupted, added, corrupted, you now have different slopes of
Yep.
and you know what there's a point in time and you know happened that before this time the diagonal was this way and after this point in time the diagonal was that way.
Uh-huh.
And it does all that.
Yeah, so the question was about multiple expansions and the impact of that. So you were asking about the impact on reconstruction, which is actually pretty straightforward because for reconstruction, all that you really need to know is the original size. Originally it was 4 wide, and I know that now I'm 7 wide, so I got to try all as if it was 7, 6, 5, 4 wide. So I showed a slide where I said, oh, new writes go to use the new physical width, and so you have a better data to parity ratio. For that, you actually have to know when the expansion happened so that you know this block has this data to parity ratio versus another. And so yeah, we keep track of a little table that's for this device, the expansion to RAIDZ to 7 wide happened in TXG X. And for any other expansions would also be in that table. But yeah, we keep that forever. That's like a totally trivial amount of metadata, so not a big deal. I mean, way less of a big deal than everything else I mentioned here, which is why I didn't.
Complexity of reconstruction seems insane.
Yeah, it is.
All right, I'm gonna come yank them off.
Okay.
For real now. Thank you very much.
Yeah. Yeah.